Welcome to topic 10.1. Here we will introduce the idea of equilibria, and especially dynamic equilibrium, and how we use this principle to describe reversible reactions in chemistry. You will have come upon the term equilibrium before, I'm sure. There are many contexts where we use this word equilibrium to indicate a balance between two things. In physics, an object is in equilibrium if it's in a state of balance. For example, a stack of books is in equilibrium. All the forces acting on the books cancel each other out. Also, a ruler that is suspended at its center of gravity will be perfectly balanced and, if disturbed, will eventually return to being perfectly still and stable. In this case, all of the turning forces acting on it will cancel each other out. We would say that the meter stick is in equilibrium. These are all examples of static equilibrium. It's called this because these systems are in equilibrium because nothing is moving. The system is static. We also have, however, systems that we would describe as being in dynamic equilibrium. Still balanced, but, as the name suggests, things are now moving. The system is not static. Take, for example, a fish swimming upstream in a river. If the river is flowing downstream at the same rate as the fish is swimming upstream, then to a distant observer it will seem that the fish is not moving. But of course the fish is moving. It's just moving at the same speed as the river and making no progress. We would say that the system is in dynamic equilibrium. Similarly, a man walking on a treadmill at the same rate as the treadmill is moving will remain in the same spot. If you could not see his legs moving, you would not know that he was moving at all. As before, the two motions cancel each other out to give us a state of dynamic equilibrium. A dynamic equilibrium, then, is an equilibrium where to the outside observer everything appears to be static, but in fact, if you look closer, things are actually moving. They just happen to be moving at the same rate, such that they cancel each other out to give us this state of equilibrium. We see examples of dynamic equilibrium everywhere in chemistry. Let's consider the example of a soft drink. These drinks are carbonated, meaning that they have a lot of carbon dioxide dissolved in them. Before the bottle was originally sealed, the pressure at the top of the bottle would have been the same as the atmospheric pressure outside the bottle. This is because any carbon dioxide that comes out of solution can leave the bottle as it's open. It is not a closed system, and so the pressures will equalize. However, from the moment the bottle is sealed, as carbon dioxide comes out of solution, the pressure will increase at the top of the bottle. Initially, the pressure is low, and carbon dioxide is mostly coming out of solution. But as the amount of carbon dioxide accumulates and the pressure increases, it will increasingly be pushed back into solution. The rate at which it goes back into solution will increase as the pressure increases. Eventually, the rate at which the carbon dioxide is coming out of solution will be equal to the rate at which the carbon dioxide is going into solution, and we will have reached a state of dynamic equilibrium. This is known as a physical equilibrium, since there are only physical changes happening. There are no chemical reactions. But we can see many of the conditions and characteristics of the equilibrium state in this simple example. The system must be closed for equilibrium to be reached. This means that there is no exchange of matter between the system and the surroundings, only an exchange of energy. In other words, nothing can escape. If you open the bottle and leave it, all of the gas will eventually escape the drink, and it will go flat. The dynamic equilibrium can only be established when the bottle is sealed. When there is a dynamic equilibrium established, the macroscopic properties are not changing. Things like the concentration of the reactants and products, colors, pressure, anything that you can think to measure is fixed and constant. This in turn is because the rate of the forward and the reverse processes are equal. Carbon dioxide is leaving and entering the solution at the same rate, so there is no change in the pressure and the amount of carbon dioxide dissolved. They are both constant. The same principles can be applied to dynamic chemical equilibria, where we reach equilibrium through chemical reactions rather than through physical changes of state. For simplicity, we tend to just refer to this as chemical equilibrium, dropping the dynamic as it's understood. As we've seen up to now, most reactions run to completion. These reactions are called non-reversible reactions. Almost all of the reactants are converted into products. A typical graph like the ones we have seen before in rates of reactions is shown. The reaction starts with just reactants present, and as the reaction proceeds, they are all converted into products, until at the end, there are only products present in the reaction mixture. The reactant curve has reached zero. Note that since both these curves describe the same reaction, they have to have the same slope at any moment in time, as shown by the tangent, and they will finish at the same time. This makes sense since products are being produced at the same rate as which reactants are reacting. Note that the reaction is fastest at the start when the reactants have the highest concentration, and it decreases over time as the concentration of the reactants decreases. Some reactions, however, don't go to completion in this way. In some reactions, as the products are formed, they react to change back to reactants. This is what's called a reversible reaction, and it's always indicated by double arrows as shown. We have a forward reaction where the reactants change to products, and we have a reverse reaction where the products change back to reactants. This gives us a different curve to before. Now, as you can see, the reactants do not go to zero because they are being reformed from products. What we do see is that the reactant and product curves plateau at the same time, as before, to show the reaction has reached completion. But here, there is still a significant concentration of both reactants and products present. In other words, we have reached chemical equilibrium, where the reactants and products are being formed at the same rate, and both are present in the final equilibrium mixture. We can see all the characteristics of the equilibrium state here again. The system is closed if none of the reactants and products can escape the reaction mixture. This needs to be the case to reach equilibrium. At equilibrium, the concentrations of the reactants and products are not changing. You can see this by the flat curves. They are fixed and constant because the forward and the backwards reactions are continuing to happen, but at the same rate. And so reactants and products are being consumed and produced at the same rate, such that there is no change at all in their concentration. This is the key feature to recognizing chemical equilibria. Though it might appear like nothing is happening from the outside, since concentrations, colors, pressures, and so on are not changing, both the forward and backwards reactions are still happening, and will continue to happen for as long as conditions do not change. Because the forward and backwards reactions are happening at the same rate, nothing seems to change, but it is a state of dynamic equilibrium, not static equilibrium. Note that the curves representing concentrations of reactants and products will always plateau at the same time point. This will show you when you have reached chemical equilibrium, since their concentrations are constant and unchanging now, which can only be because the rate of the forward and the backwards reactions are equal. Finally, this brings us to the definition of chemical equilibrium. This is very commonly asked in the exam, and is often asked in different ways. You are sometimes asked to define chemical equilibrium in terms of rate. Here, they are looking for you to identify that at equilibrium, the forward and the reverse reactions have the same rates. If you are asked to define chemical equilibrium in terms of concentration, you need to identify that at equilibrium, the concentrations of the reactants and the products are not changing, or that they are constant. If you are simply asked to define chemical equilibrium, you should make both of these points. Sometimes you can also be asked to explain why chemical equilibrium is dynamic. Here, of course, we need to say that the reactions have not stopped, but that they continue to happen. That's it for topic 10.1. Have a go at the questions.